about it. So here's Chebyshev's theorem, and it has to do with the standard deviation. And basically what it says is that if you have if you know the mean for your data, so here we can see the mean, so we know the mean, and we also know the standard deviation, then Chebyshev came up with this kind of pretty good result, which is that if you go a certain distance from the mean, here's the mean, if you go a certain distance from the mean, he can tell you that you will have at least a certain amount of data in that range. So here, how far are they indicating that they're moving away from the mean? So here's the mean. How far are they moving away from the mean? Well, they're moving k standard deviations. Remember, the standard deviation is just a number that you will calculate from your data, so you can move 2 times that number, or 3 times that number, or 5 times that number, or whatever it is, away from the mean. So you can move k standard deviations away from the mean in this direction to the right, and you can also move k standard deviations from the mean to the left. That would be over here. Okay, forget about the shape of this thing here. Just ignore it. And Chebyshev says that if you go a certain amount here and here, he'll tell you how the minimum amount of data that has to be within that range. Okay, that's what Chebyshev's theorem says. Now, the answer to that, the actual amount that he'll say comes from this statement here. But the idea is, whatever he's going to say the actual number is, he's going to tell us that if we go a certain distance this way and a certain distance this way from the mean, he'll say that, at least 25% of the data is in that range, or at least 50%, whatever it is. Okay, so let's see. Do we have any data here? No data. All right, so anyway, so instead of giving you data, they just say, okay, here's an example where they tell us the mean and the standard deviation. Okay, they don't ask us to calculate it from the data, they give it to us. So this is what? For blood pressure of women. Okay, that sounds pretty high, doesn't it? 187, isn't that super high? For blood pressure? What? High blood pressure, yeah. It's just kind of weird. Sounds really, really high. But anyway, okay, suppose the mean for some group of women blood pressure was 187. And the standard deviation, maybe this is some other units, I don't know, but anyway, the standard deviation was 22. So if you go 1 standard deviation above the mean, what blood pressure is 1 standard deviation above the mean? Can somebody tell me that? 1 standard deviation above the mean is what? Somebody tell me? So the mean is what? 187, and the standard deviation is how many units? 22. So if you go 1 standard deviation above 187, what do you get to? You get to 89, 199, 209, right? So what is 1 standard deviation above the mean? 209. Okay, what is 1 standard deviation below the mean? You have to subtract 22, so what's that? 85, 75, 65, right? 165, so what was the range again? 165 to, what was it? 209, I think? 209, was that right? Okay. And then, of course, if we want to go 2 standard deviations, we have to do that calculation again, right? So, okay, so what do? They're doing 2, so we have to do 2. So 2 standard deviations is plus 44 and minus 44. So plus 44 gives us what, 191, 231, right? Is that right? 231, and minus 44 gives us what? 143. Is that right? So in that range, let's see, they should have the numbers here actually, right? Yeah, here they are. 143 and 231. Okay, does everyone understand these two numbers? Okay, what are they? What are these two numbers? 143 to 231 is 2 standard deviations below to 2 standard deviations above. So Chebyshev's going to say, oh, I can tell you that at least something amount of the data is going to be in that range. And the actual number that he's going to say comes from this formula, which is here. Here. It's 1 minus 1 over k squared. So k was 2 standard deviations, k was 2. So 1 over 2 squared is what? 1/4, right? 1/4. So 1 minus 1/4 is what? 75%, right? So he's going to say, I know that at least 75% of all the data will be in there. Let's just try an example. Let's use Excel. I guess maybe we should use R. But it's easier to use Excel. I'm going to use Excel. I shouldn't do that. I should get us to use R, but I'm going to use Excel. Okay, now let's take some data. Let's make some data, let's say, well actually no, let's use R. Okay, everybody open up R. Might as well try and get used to R, right? So everybody open up R and generate a sequence of data, and let's use the same data, everybody. So let's do generate a sequence of data from 1 to 40, from 0 to 40, and with a step of 2. So it means 0, 2, 4, 6, 8, up to 40. Okay, how do you do that? And give it a name. Let's call it X. How can I do that? So I want X equals something. What should it be? Anybody, any genius around here? Any R geniuses here? Do you remember? I'm sure we did it. We need a function. What function? What? Yeah. Sequence. And first you put the lower number, so 0. Then you put the higher number, so 40. And then you put the step, so 2. Okay, print it out, X. Does it work? Yeah. Okay, now calculate the mean of this data and call it mean. Okay, and then calculate the standard deviation and call it SD. How do you calculate the standard deviation? SD, right? Okay, let's see what they are. Okay? All right, now, so, unfortunately the mean is pretty, is not, I guess that's about right. Standard deviation is pretty big, actually, but okay, that's what we have. All right, so if I go one standard deviation up from the mean, where am I? If I go one standard deviation up from the mean, where am I? 20 plus 12.4, right? So it's like 32.4, right? If I go one standard deviation down, where am I? About 8, right? Or 7.5 or something like that, right? Okay? All right, everyone understand? How about if I go 2 standard deviations up, what am I? I'm up to 22, so I'm up to 44, right? So I'm actually outside of the range of our data already, right? And if I go 2 standard deviations down, where am I? Negative something, right? -2 or -3, right? So I'm actually outside of the range of our data there as well, right? Everyone understand? Now what does Chebyshev say about if we go 2 up and 2 down? He says this formula, right? What is this formula? 1 over 1 minus k squared. So k, I just did k was what? 2 standard deviations, so 1 over 1 minus 1 over 2 squared means 1/4. 1/4, 1 minus 1/4 is 75%. He says at least 75% of the data will be in that range. From, what was the range again? Like -2 up to 44 or something like that, right? So he says at least 75, but in fact, how much is in our range? All of it, right? All of the data is in that range, but that's okay. He didn't say exactly 75%, he said at least 75. Okay, does everyone understand how this works? Okay, so that's Chebyshev's theorem. Okay, good. All right, that's as far as I'm going to go with chapter 3, and I'm going to go on to chapter 4 now, called probability. So, in probability, it's important to understand a few words, and I mean, of course, you probably know these words, at least the first 2 of them. You know this word, and you know this word, of course, but they're used in a special way in probability, and it's good to understand these words as they're defined in probability, not because you should just learn a bunch of words, because by learning these words, it gives you a framework to do probability problems much more easily. Okay? So if I asked you, for example, when you roll a die, when you roll 2 dice, what's the probability of getting a 5, the sum equal to 5? Right? What's the probability that the sum of those 2 dice is 5, right? When you have 2 dice, you could have a 1 on the first die and a 1 on the second die, right? So the sum would be what? 2. Or you could have a 1 on the first die and a 2 on the second die, so the sum would be what? 3. Or you could have a 6 and a 6, so the sum would be what? 12, and so on. So the sum can be various values, right? So now I'm asking, what's the chances that the sum is equal to, what did I say, 5? What? Sorry?
The chance to get a sum of 5 is 1/9.
1/9, maybe. But it's not so easy to do that. So what I want to do is give you a method to think about probability problems and a framework to think about them so that it becomes easy. And to do that, you need to know these words. Okay? So let's learn these words because they really do, this framework really does work well. So, okay, first of all, what do we mean by the word experiment? So, how about when you think of the word experiment, what image, what picture comes into your mind? Just the first flash, first image that comes into your mind.
Laboratory.
What?
Laboratory.
Laboratory, yeah, good. That's what comes into mind also. Let's look at images and see what we get. Yeah, I think of something like this, or something like this, or something like that, or something like that, not like that. Or like I think of like pouring two chemicals together and getting some kind of explosion. Okay, so experiment, that's what we think of, right? But in probability, it has a special meaning. And it means performing some action where you don't know the outcome. Where you don't know the outcome. Is that reasonable to say that that's what an experiment should be? Well, put it this way. If you did know the outcome, would you call it an experiment? If you knew the outcome, if you knew what was going to happen, would you really call it an experiment? No, not really, right? So that's reasonable, right? So that it's something where you don't know the outcome. Okay, so anything where you perform some action and you don't know the outcome, we'll call an experiment. So I can call this an experiment. I toss this coin, and I check to see what's on the top, right? So I don't know what it is, so that's called an experiment, okay? All right, so we have this notion of an experiment, and then we have what we call the outcomes of the experiment. So in probability, we want to describe the experiment in such a way that we know precisely what kinds of outcomes they're going to be. So when I said, I flipped this coin, and then I said that's an experiment, that's not really the full description of the experiment, it's just flipping the coin. That's really not good enough. I have to say something like flipping the coin and recording whether it's heads or tails. Okay, because I could just flip the coin and record the color of the coin, right? Or so I could flip the coin and record the temperature of the coin, or how high it was, or right? Or lots of different things. But so you have to describe the outcomes that you're interested in when you say what the experiment is. So it's not just flipping the coin, it's flipping the coin and recording the outcomes as to heads or tails. Because I could do this also. I could take two coins and flip them, and then what am I interested in with those two coins when I flip them? So it could be different things. For example, one person might say, oh, I'm interested in the sequence of heads and tails, or I shouldn't say the sequence, the pair of heads and tails. So did I get HH, heads, heads? Or did I get HT, heads, tails? Or did I get TH, so I could distinguish the first coin and the second coin? Or I could use two different types of coins, like a 10 yen coin and a 1 yen coin. So did I get HT or did I get TH? That could be different, right? So that's one thing that you could be interested in. That would be one experiment based on flipping two coins. But a different experiment would be counting the number of heads. Okay, so that would be called a different experiment. So even though I'm doing the same action here, you also have to state what you're recording or what you're observing in order to completely identify the experiment. Okay? So if I toss two coins, then I can say toss two coins and record the sequence of heads and tails. So I would say the experiment is tossing two coins and recording the sequence of heads, could call it H, and tails, could call that T. Or I could say the experiment, a second experiment, experiment 1, experiment 2, could be tossing two coins and recording the number of heads. Okay? Those are called two different experiments in this language. Okay? So recording the number of heads, or the sequence of heads and tails. So the outcomes for this experiment, what kinds of outcomes, what could you get in this case? We just said you could get heads, heads. You could get heads, tails. You could get tails, heads, and you could get tails, tails. Okay? And for the second experiment, which seems like it was the same experiment, but it's different. We call it a different experiment. What could you get? You could get 0 heads. You could get 1 head. And you could get 2 heads, right? So those are the outcomes for experiment 2. And the outcomes for experiment 1 are a different set. Okay? Everyone understand? So the outcomes of the experiment. Now, you have sets. We won't go into this, but you have 2 sets A and B. You can talk about the union of 2 sets, and you can talk about the intersection of 2 sets. Everyone know about that? Right, so the union would be everything here, that's the union, and the intersection would be just that part, right? Right, we talk about that, right? And also you can talk about one more. A prime, also sometimes written as A bar or A C, that means the complement of A. The complement of A means everything outside of A. So everything outside of A, here's A, everything outside would be here. Okay, so we have these 3 called operators for sets. Okay, union, intersection, and complement. Okay, so I assume you know about those. Now, so that's about sets, right? So here, I want to know what are the set of all the outcomes for experiment 1. What's the set of all the outcomes? Well, we just listed them, so we don't have to think very hard, right? They're right there. But I use the word set, and when we use the word set, we should put these kinds of brackets around them. Okay? The set of all the outcomes. Okay? And here, the set of all the outcomes for experiment 2, right? We use those kinds of brackets for sets, right? And when we talk about the set of all the outcomes, the set of all possible outcomes of an experiment is called the sample space for that experiment. It's called the sample space. And I think in our book, it's denoted with a capital S. Okay? So the sample space is just what? The set of all the outcomes. So what's a sample space for experiment 1? Right here. Right? There are 4 elements in it. Right? So this is called S. Okay, and what's the sample space for experiment 2? So that's here. Okay? Everyone understand? Sample space means the set of all possible outcomes. How about if you tossed 3 coins? So the experiment was, experiment 3, let's call it, is toss 3 coins, but that's not a good enough description of the experiment yet, right? I have to say what I'm going to record. So, and record, let's say I say, and record the sequence of H and T. Okay, so what could I get if I toss 3 coins and I record the sequence? Or let's say I toss 1 coin 3 times and I record the sequence. What could I get? H on the first, H on the second, H on the third. Or I could get H on the first, H on the second, but T on the third. Or I could get what? Or I could get like H. So instead of, so this time I got 1 T, right? But instead of having the T at the last position, I could have the T where? A single T at the second position. Or I could have a single T at the first position. And then I could get, instead of 2 heads and 1 tail, I could get 2 tails and 1 head. So I could have that head at the last position. Or I could have it where? At the second position. Or I could have it where? At the first position. Or finally I could have what? All tails. Right? And so this is called what? The sample space for this experiment, for experiment 3. Okay, the set of all the possible outcomes. Okay? How about if I roll 1 die and count the number of dots on the top face, which is normally what you would do, right? You roll a die, everybody knows a die means something like this, right? Oops. And so on, right? That's a die. So roll a die and count the number of dots on the top face. Okay, let's call that experiment 4. Then what's the sample space for experiment 4? The set of all the possible outcomes. One possible outcome is that there's only 1 dot on the top face. Or there could be 2, 3, 4, 5, or 6. Right? So that's another experiment with another sample space. Or we could say, another one would be, how about this one? Experiment 5. Toss toss 5 coins and count the number of, okay, let me explain something. In statistics sometimes, or I don't know, in some places they talk about the number of runs. So like if you have like this, H, 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 T, 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 H, 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 T, H, T, T, T. Suppose you had that sequence of heads and tails. We'd say, oh, here's a run of H's, a run of heads. And then here's a run of, it means like a repetition of tails. And then there's a run of H's again. And then there's a run of, and then even 1 T is referred to as a run of tails. Okay? And so you could do that. Okay, so how many runs are there here? Here's a run, that's called 1 run. So here's a run. And then here's another run. And then here's another run. and then this is actually called a run, and this is actually called a run, and this is actually called a run. So there's 1, 2, 3, 4, 5, 6 runs. Okay? Just sometimes we're interested in that. I don't know where exactly, but maybe in communication theory or something like that, when you're talking about, I don't know. I'm not sure whether you're interested. Engineers are interested in this kind of stuff. So, so here, toss 5 coins and count the number of runs. Okay? So you can't have 0 runs, right? That's impossible, right? You can't have 0 runs. So the sample space does not include 0. You could have 1 run, which would mean what? Like all heads or all tails. That would be 1 run. Okay? Or you could have 2 runs, 3 runs. What's the most we could have? Heads, tails, I guess 5. We could have 5 runs, right? So it could be 1, 2, 3, 4, 5. Right? So that's the sample space for that experiment. Okay, so what is the experiment means again what? Performing some action where you don't know the outcome. And then the sample space is what?
The collection of all points.
Right, it's the collection, the set of all possible outcomes of an experiment is called the sample space. Okay? Now, it's not always true, but oftentimes the probability, one more word. Event, we need one more word. So we have a couple words so far. We have experiment and outcome and sample space. And then we have one more called event. So what does the word event mean? And of course in this context, in this math context, we're going to give it a special definition. But in general, what does it mean, the word event? What does it mean, event? Or how about use it in a sentence? Event. How to use the word event in a sentence, just in a common sentence. What does it mean? What does the word event mean? How about in a sentence? Okay. We're having a big event next week. Okay, that's one way to use it, but that's not what I mean. Another one? Okay, I want to use it in this way. In the event of a fire, everyone should leave by this door. Or, right? Something like that, right? In the event of a fire. Or another one. In the event that when you roll a die, you get a 3, then you win $100. Okay? Or another one. In the event where you get a run of 3, where a run of 3 occurs, you'll get $100. Okay? In the event that when you roll 2 dice, the sum is 12. Okay? In the event that when you roll 2 dice, the sum is 12, you'll get $100. Right? So, or in the event that you get an even number for the sum, you get $10. Okay? Right? You understand? Or, how about in the event that the die is even, you get $5. In the event that the die is less than 5, you get $5. Or you get $2 or something, right? You understand how I'm using this word event? So make up your own sentence for event. Go ahead and make up a sentence. Somebody? Somebody? Make up a word event. A sentence with the word event in it. Anyone? I mean, I just made up a bunch of them. You can use a very similar one to what I just used. Anyone? Nobody?
An event I win lottery.
Yeah, but I want to say the particular thing that causes you to win the lottery. So an event that the number 777 comes up, then I win $100 or something. How about more in terms of this, just these examples that we used? So just make up another one like I did, having to do with either the dice or the coin or something like that. What would that be? You can do it, right? It's not so hard. In the event that you get a 4, right, then you get $20. Okay, anything like that. Okay, so now let's try and give a general definition for the word event in this context, not in the general sense of the word event, but in this math sense. So relate the definition to the concept, the word sample space. Can you do that? Can you relate it to the concept of sample space? Can somebody do it? What can we give a definition? Anybody give a definition for event in terms of sample space? No? Okay, what did I just say? Let's say, give some examples of events. E1, E2. Okay, so somebody tell me one of the events that we just mentioned. We just mentioned about 6 of them.
You win $3 if you get 4.
No. The event is getting a 4. What you win is separate from that. Okay? So what's the event? Getting a 4. Getting a 4, and we should say that we should give the context. We should say the experiment that we're referring to. So rolling a die, right? When rolling a die. Okay, so another one. Give me another one. So what you win is the amount that you win is a separate idea. Just give me an example of an event. Okay, great. Getting 777. But what's the game? Or what's the experiment? Okay, so you're playing some game. How about more simple one? More like this, the simple ones that we've referred to, the experiments that we've been referring to. Because that we didn't really talk about that experiment.
Flip a coin and
Okay. Flip a coin and get heads. Getting heads, right? And I should say when flipping a coin, right? Okay, good. How about another one? experiment. I'm sorry, another event. Just one more. So think of a particular experiment and then an event. So we have a bunch of experiments that we've already described, so choose one of those and then an event.
Getting to and rolling a die.
Getting a 2, great. Getting a 2 and rolling a die, that's another event, right? Okay, so we have some examples of events. Now let's see if we can formulate a definition for this word. So what were some of the examples? He said, when you roll a die, what's the sample space? 1, 2, 3, 4, 5, 6. And what was the event he just said?
Getting a 2.
Getting a 2. How about another event for the same experiment? What? Getting a 4. How about another event for the same experiment?
Getting 3.
Getting a 3. Okay, how about another event for getting an even number? Right? Getting an even number. Even number, right? Okay, so all of these are events with regard to that experiment, right? So what can we say is a general definition of event? So here's what we're going to say. So we said getting a 2, somebody said getting a 3, I said getting an even number, right? These are all different events. Is this an event? Getting an 8. No, right? Right? That's not an event for that experiment, right? How about getting a 3.5? Is that an event for that experiment? No. So what must an event be? It has to be a collection. It doesn't have to just be one. It can be a collection of elements from the sample space, right? Or specific, or we'll just make it a little bit more precise. We'll say an event is any subset of the sample space, right? Any collection or any subset of the sample space. Okay, is that clear? So we'll keep it in the framework of sets, right? So if we have a sample space 1, 2, 3, 4, 5, give me one subset of this. So E1 could be 2. Right, that's a subset of S, right? E2 could be 5. That's another subset, right? So what are the different subsets? How many are there? You could have each one of these individually. Whoops. You could have each one of these individually, so that's 6 subsets. So those are 6 different events. And then you could have pairs of them. Like you get 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. Those are all separate events. Then you could get 2 and 3, 2 and 4. Those are all separate events. Now we don't say that this 1 and 2 is different than 2 and 1. We don't say those are different, right? Because the event that you get at this, we're talking about doing the die one time, right? Like I said, the event that you get an even number. How many times was I talking about tossing the die? One time, but you can still have 3 elements in the event, right? Right? It just means if you got a 2, a 4, or a 6, you would say you got an even number, right? So we have to list 3 elements even though it's only one event, right? So the fact that there's more elements in the event doesn't mean you're doing the experiment more than one time, right? So that means this is the event of getting a 1 or a 2. So I don't say this is different, right? This is the same event, getting a 1 or a 2, right? It's the same thing, right? So these are not considered different, right? Okay? So, so anyway, how many different events are there for this experiment? That means how many different subsets are there of this set, right? How many different subsets are there of this set? And you can show, it's possible to show, that if you have 6 elements in there, there are going to be 2 to the 6th different subsets. 2 to the 6th is what? 2 to the 3rd times 2 to the 3rd.
60.
2 to the 3rd times 2 to the 3rd. 2 to the 3rd is what? 8. So 8 times 8. So there's 64 different events associated with this experiment. Okay, 64 different possible events. After that, you just repeat yourself. You're not making up new events. Okay, so like we said, you could have just a 1, just a 2, just a 3, just a 4, just a 5, just a 6. That's 6. You get 1 and 2, you get 1 and 3, you get 1, those are another. And you can have like groups of 3 of them and groups of 4 of them and so on. Altogether, it turns out that there are going to be 64 events. Okay? Now, the next thing is, so finally we get to the idea of probability. Okay? So now we ask a question like, suppose E1 is getting an even number. Okay? Getting an even number. So what's the probability? Then we can say, then using the word probability makes sense in this context, right? I can say, what's the probability of E1? What's the probability of getting an even number? What's the answer to that? I think everybody knows what the answer to that is. What is it? A half, right? When you roll a die, what's the probability that you get an even number? It's a half. But I'd like to find a way to calculate that. Okay? Or, how about this one? E2 getting a number less than 5. Okay, getting a number less than 5. Or how about E3? Getting a 4. Getting a 4. Okay, so let's write each of these events in terms of how they look as sets first. So E1 is what as a set? Two, 4, 6, right? That's that event. E2 is what as a set? 1, 2, 3, 4. E3 is what as a set? Just a 4, right? Okay? Now, one more thing we need, one more notation we need. When we have a set, I use this number, there are other things you can use, but if I have a set, let's say A equals 4 star smile 17 Z, how many elements are in that set? 5, right? So we write this, n of A equals 5. So n means the number of elements in the set. Okay, the number of elements in the set just means the number of elements in the set. Okay, so if I said, what's n of E1? How many elements are there? 3. What's n of E2? How many elements are there in E2? 4. What's n of E3? Just 1, right? The number of elements in the set. And let's remind ourselves, what's the sample space for this experiment that we're talking about? So what's the experiment again? Rolling a single die. So let's remind ourselves, what's S? When you roll a die and recording the number of dots on the top face. So what is it? 1, 2, 3, 4, 5, 6, right? So one more thing, what's N of S? 6, right? Okay, now, again, what was E1? Getting an even number. What's the probability of E1? Everybody knows that. The answer is a half. But is it a coincidence that the number of elements in here is how many? 3, and the number of elements in here is how many? 6. Is it a coincidence that 3 over 6 is equal to a half? No, because why is it a half? Because each one of the, one more thing, what's the probability of this one? What's the probability of getting a 4 when you toss a die? 1/6. How did you know that? Because there are 6 outcomes, and one more thing we have to say is that they're all equally likely. Right? They're all equally likely. If they weren't all equally likely, and in fact, if I have a real die, are all the outcomes perfectly equally likely? No, because no die is made perfectly, right? So they're going to be unbalanced to some degree or another. So the probability of one side is going to be not exactly the probability of another side. But we assume what? That they're all equally likely, even though in fact they're not. Okay? So that's why we said that the probability of E3, the probability of getting a 4, is 1/6, because we're assuming they're all equally likely, right? And there's 6 possibilities, so the probability of any particular one is 1/6, right? Is that, so if I said a 4 and a 5, if I said E3 was 4 and 5, what would be the probability of that? Well, it would be the probability of a 4 plus the probability of a 5. What's the probability of a 4? We already said 1/6, and what's the probability of a 5? 1/6, so the probability would be what? 2/6, or 1/3, right? Okay, so what's this formula we're generating here? First of all, let me make this notation. We're going to ask, what's the probability of E3? We're going to write it like that. Again, what was the answer to that? E3 was getting a 4. What's the probability of that? 1/6. So we're going to put 1/6. So this notation means the probability of that event. Okay, now I also had, what was this one? E1. E1 was which event? Getting a 2, a 4, or 6, which is can also be described as getting what? Getting an even number. You can describe it either way. So what's the probability of that? We already said 50%, or 1/2, right? Or 3 out of 6, right? 3 out of 6, right? So what is the formula that we're using actually here? We're saying that the probability of event E1 is equal to, how many elements are in E1? 3, divided by how many elements are in the sample space? 6. 3, 6, right? So we're saying it's n of E1 over the whole sample space size. It's the proportion of elements in E1 to the size of the sample space, right? That's the formula we're using. So how about this one? What's the probability of E2? Again, it's the ratio of the size of E2 to the whole sample space. So that's what? N of E2 over N of S. Right? So in general, the definition, in general, the calculation for the probability of an event so we can say if E is some event, and if associated with some sample space S, then the probability of E is equal to what? The size of E compared to the size of S, right? The number of elements in E compared to the number of elements in S, right? So we write N of E over N of S. Okay, does that make sense? Is that clear? So let's use that to do the first question I asked. So that was roll 2 dice and sum the what do I say? And record the sum on the 2 top faces, right? The number of dots. Record this. I guess I could be really wordy about it. Record the sum of the number of dots on the 2 top faces, right? That's really unnecessarily wordy, but the number of dots on the 2 top faces. Okay? No, I made a mistake. Wrong. Don't do that. Okay. Record the sequence of numbers. Okay? So first of all, let's write the sample space in this case. And don't forget, we have this formula now here. Okay, don't forget that. But my question was, when you roll 2 dice and you do this, remember what was the original question I had? What was the probability of getting a sum of 5, right? Remember that? Okay, let's see if we can answer that now in a methodical way by doing all these steps. So the first step is to state the experiment, and the next step is to make a picture, get a feeling for what the sample space is, or write out the sample space. So I want to write the sample space. So I could get a 1 on the first die and a 1 on the second die, right? Or I could get a 1 on the first die and a 2 on the second die. Or I could get a 1 and a 3. Or I could get a 1 and a 4, get a 1 and a 5, or what? A 1 and a 6, right? But then, of course, I could get a 2 on the first die and a 1 on the second. Or I could get it, let me stop writing these parentheses because it takes more time. I could get a 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6. But that's not good. I'm still not limited to that. I could do what else? 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. And that's the set of all possible outcomes, right? So that's called the sample space, right? Now, one thing that I didn't mention, but for this formula to work, all of the outcomes have to be equally likely. Otherwise this formula doesn't work. Okay, like if you had a die, a single die, and they weren't all equally likely, then you couldn't just count up how many are in your event and then, you know, do the calculation from that, because each die, each outcome could be slightly differently likely, and then it doesn't work anymore. Okay, so you have to assume that all the outcomes are equally likely, otherwise this formula doesn't work. Right? Like suppose you had a die where the 6 like came up 90% of the time for some reason. Right? Then you couldn't just count the number and get the probability. It wouldn't work, right? Right? So it has to be a balanced die. So let's assume that we have 2 balanced die here. Now, let me ask you, would you say that this outcome is more likely than this outcome, or this one is more likely than that one, or are they both equally likely? 3-2 or 4-2? Are they equally likely? Is the top one more likely than the bottom, or is the bottom one more likely than the top? They're equally likely, right? There's no reason to argue that this one is more likely than this one, and just the same, there's no reason to argue that this one is more likely than that one, right? So we don't have any reason to say that one is more likely than the other, so they're equally likely, right? We can say they're equally likely. So in fact, every one of these points here are equally likely points, right? Every one of these combinations are equally likely, right? And how many combinations are there here? How many rows are there? 6. How many columns are there?
6.
So how many elements are there?
36.
36. How can I express that with the n notation? N of S equals 36, right? Right, the number of elements in the sample space is 36. Okay, now, what was the question that I asked at the beginning? What is the probability of what? Of getting a sum of 5, sum equal to 5. Of getting a sum equal to 5. Right? Now, whenever you ask a probability question, you're always asking the probability of some event. So, I'm asking a probability question here, so I'm asking the probability of some event. So what is the event that I'm asking about in this question? I'm asking what is the probability of an event. So what is the event? There's the event, right? What is the probability of the event? Right? So there's the event. So what is the event? Getting a sum equal to 5, right? But to make this clearer, remember we said events have a certain relationship to the sample space. What's that relationship? I erased it, but we said that an event has to be a subset of the sample space. Well, we've already gone to all, I have already gone to all the trouble of writing out the entire sample space. So now I can easily picture subsets of it, right? So, so where are they? Or where's the particular one that we're interested in? The event of getting a sum equal to 5 better be a subset of S. So where is it? Which subset is it? Which set of points, or set of, set of, I'll call them points. Which set of points is it? So is this in there? Is this part of that event? No, because that's not, the sum of these is 9. Is this in it? No. Is that in it? No, is that in it?
Yes.
Yes. So I'll include this one. Where else? Is this in it?
No.
Is this in it?
No.
Is this in it?
Yes.
Okay, I'll include that. Is this in it?
Yep.
Is this in it?
No.
Is this in it? No. Is that in it?
No.
Is this in it?
Yes.
Are there any more?
No.
No. So that's the event, right? It's a subset of the sample space. Did I give this a name? No. Let's call it E10. Just, I don't know, call it something. So that's E10. So E10 is that event. Okay, now we can use the formula here. So let's see what the answer was. The question was, what was the question? The probability of E10, right? And our answer is going to be a ratio, and the bottom is going to be the size of the sample space, which we already said is what?
36.
36. And then we need n of E10. So how big is E10? How many elements are in E10? 4. So we get 4 over 36, which is 1/9. So what's the probability of getting a sum of 5? 1/9. How about if I make another event, E9 is getting a sum of 4. So where's that in this subset? So is that in it? Is that in it? Is that in it? Are there any others? No, so it's these. So this is called E9. And how big is E9? How many elements are in E9? 3. So what's the probability of E9? 3 divided by the size of the sample space, the same as before. 3 divided by 36, so 1/12. What's the probability of getting a sum of 3? 2 out of 36, which is 1/18. What's the probability of getting exactly 2 ones? It's 1 out of, so the probability that the sum is 2 is 1 out of 36. What's the probability that the sum is 6? This one, right? Call that E8. What's the probability of that? 1, 2, 3, 4, 5. Right? 5 out of 36. What's the probability that the sum is 7? 1, 2, 3, 4, 5, 6 out of 36. 1, 6, right? What's the probability that the sum is 8? 5 out of 36. What's the probability that the sum is 9? 4 out of 36. What's the probability that the sum is 10? 3 out of 36, and so on, right? So what's the most likely sum? Which is the longest set? 7, right? So that's the probability of getting a 7, the sum, getting a 7 is the most likely sum, right? Getting a 7 is the most likely sum. Now, are these diagonals the only possible subsets of this? No, of course there are millions of, so many different subsets of this, right? You could do like this, and then this, and this together. That's a subset, right? They don't have to be any particular pattern. All kinds of possible subsets. In fact, according to the formula that I gave you earlier, the number of subsets is 2 to the 36, which is a lot. And it's a big, 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 big number. So just here I have one, just a bunch of them, only about 10 different subsets that I've outlined here, but those are just, ones that I've focused on because I'm interested in those. Okay, everyone understand? So what's the formula that we're using? So now, like I said, as I said, using these concepts of experiment and sample space and event, using those concepts makes it pretty easy to do problems. You saw that we could do all these problems now with those concepts. Okay? So if you can, read a problem and they ask for the probability of something, if you can go back and say, okay, what's the experiment here? So that means what's the sample space here? And then what is the specific event that they're talking about? And what's the relationship of the size of that to the size of the sample space? You're going to be able to do it really quickly. Okay? So not every problem will fit into that pattern so easily. You might have to really stretch that idea to make it work for a lot of different problems. But sometimes it's worth trying to stretch it, and sometimes problems don't even need to be stretched to get them to fit into that kind of framework. So that's a very good way to do it. What happened? So let's take a look at, now, one thing is, like I said, this calculation here, there's a caveat, a warning for this calculation. What's the warning? If this die that we were talking about was unbalanced and getting a 6, at a 90% probability, not one, we said, or getting a 5, getting a 4, let's say, had a 90% probability, we said the probability of getting a 4 should be what? 1/6. Is nowhere near 90%, right? If it's not balanced, then counting up the number, like how big the event is, so suppose I said getting a 3 or a 4, the probability of that's some event. Normally we would say that's 2 out of 6, right? But if the 4 had a super high probability, it wouldn't be 2/6 anymore, right? So that doesn't work. This formula doesn't work unless all the outcomes are equally likely. Okay? So you have to have that assumption for that particular formula to work. That doesn't mean all the other stuff we said can't be useful about talking about the sample space and events, but that formula doesn't hold. Okay, now let's see what they say about all of this stuff. Okay, experiment, outcomes, sample space. So we've basically covered this. Let's see what they say. So an experiment is a process that, when performed, results in one and only one of many observations. So that's a little bit different than what I said, but okay. These observations are called outcomes of the experiment. The collection of all outcomes of an experiment is called what? The collection of all outcomes is called what? What's it called? sample space, right? Okay. Now they say that, so this is called a Venn diagram. And here we have the 2 points, heads and tails, right? This person cannot stop browsing. What is it? What are you browsing? Who is that? Who is this person? Huuninning. Who's that? Are you afraid to identify yourself? Who is it? Okay. So, we can make this kind of, to get the sample space, when you toss a single coin, we know the sample space is H and T. So, you can make this kind of tree diagram to see the sample space. That's not so clear, actually. But here, suppose we here's a, tossing a coin twice. Okay? Tossing a coin twice, what's the sample space? We said HH, what else? HT, TH, TT. How did they come up with these? They said we can do it this way. We can say, let's talk about what can happen on the first toss. So what can happen? H or T. And once you say, I got an H on the first toss, then you can say, what happens on the second toss? H or T. So if you got an H on the first, and then you go up here, you got an H on the second, then you got what? H and H. So you can break it up into what happened on the first toss and what happens on the second toss. So then you get HH, HT, you could get TH and TT. Okay? So that's a way to figure out what the sample space looks like. How about if you're talking about, suppose we randomly select 2 workers from a company and observe whether the worker selected each time is a man or a woman. So what's the sample space, they say? So in the first selection, what can you get? M or W. And then given that you got an M on the first, what can you get on the second? M or W. And so on. So you get MM, MW, and so on. Okay, they distinguish between what are called simple and compound events. So we already said that an event is a collection of one or more outcomes of the experiment. Now they distinguish between what they call simple and compound. So an event that includes only one and one final outcome of an experiment is called a simple event. So in other words, going back to here, what's the sample space here? Here it is, MM, MW, WM, WW. How many subsets are there of this? The formula I gave you will tell you that it's equal to what? 2 to the 4th. 2 to the 4th is what? 2 times 2 times 2 times 2, which is 16. So there should be 16, right? So there's 16 different events, but the ones that are called simple events only contain one of these. So you could have an event MM, right? You could have an event, what? MW, right? That's like going up here. You could have an event of just getting getting H and H. You could have an event of getting H and T. You could have the event of getting TH or TT. Those are called the simple events. Then any other events, the more complicated ones, the bigger collections, are called compound events. Okay? So there are 4 simple events here. But there are how many events altogether, we said? What was the formula I told you? 2 to the fourth, so that's 16. There's 16 events, but only 4 simple events, as they define simple events. Okay? So, a compound event is a collection of more than one outcome of an experiment, right? So not just the simple events. Okay? Okay. Okay. Now, so here we have a sample space, the sample space of these 4 outcomes, right? You could get a man and a man and a woman, so on, right? Now, here's an event. I don't know how to say it in words, but it just has MWWM and WW in it. It's a subset of the whole sample space, so it's an event. But it's not a simple event, right? It's a compound event, right? It's a compound event. Okay? Okay, here's some other examples. What's this? Some people are in favor of genetic engineering and others are against it. How many people in this room, do you know what genetic engineering means? What does it mean? I'm not sure. What does it mean? It means like using genes to, playing around with genes to affect the outcomes of, I guess it doesn't have to be people, right? Could be food, and so on, right? Okay, how many people in this room are against genetic engineering? Really? You'll never eat any food that's genetically engineered? You're trying not to, okay, good. How about, would you be against genetic engineering for medical purposes? Like to, help somebody overcome some disease or something? Sounds better, okay. All right, so anyway, so here they said in a group of people, some are in favor of genetic engineering and some are against it. 2 people are selected at random from this group and asked whether they are in favor or against genetic engineering, right? So we can record the first person as either F or A, and the second person is either F or A, right? So what's the set of possibilities for 2 people? Well, the first person could be F and the second person could be F. The first person could be F and the second person could be against. A and F and A and A, right? So we get these outcomes. So the sample space looks like, they didn't write it, but it looks like these 4, right? Now, how about this? Could we use that formula to find probabilities for this sample space? No, because there's no reason to believe that these are all equally likely, right? I have no idea. Right? We have no idea whether FF is equally likely to FA, right? We don't even know that, because we don't know the probabilities of F and A, right? So they're not, very, very unlikely to be equally likely, right? So we can't use that formula in this setting for this kind of problem. We can do other things, but we can't use that nice, very simple formula, okay? So here's an event. The event, both persons are in favor of genetic engineering. What is that? It has to be a subset of these 4. Which subset is it? FF, right? They're both in favor. The event that at most one person is against genetic engineering. At most one person from the 2. So what's that? FF? Is that at most one person is, what did they say? Against. At most one. So no one is against here. So that's at most 1. One person is against here, so that's at most 1. And one person is against here, so that's at most 1. So this is the event that at most one person is against, right? So you see how you can translate the verbal statement into a set, right? At most one, the verbal statement, gets translated into this set, right? So that's part of the trick of using this structure, is to take the problem, which is expressed usually verbally, and translate it into sets, right? Because once you do that, it can be easier. Now, still doesn't mean we can go that far and use that. Well, sometimes we can, but in this case we couldn't. Okay, so that's that one. Next one is here. So probability, what do they say here? This is such a weird thing to say, isn't it? Mathematics likes to be kind of like this, though. So what does it say? So just do you agree or recognize that this is a valid way to speak? Just the blue part here. So it's a numerical measure. That means, basically what they mean by that is that it gives you, you give it an event and it gives you a number back. Isn't that what we've been doing? Like I said, what's the probability that the event of this, what's the probability of this event, right? So I gave it an event and it gives me a number back, which is the measure of the probability of this event. So that's what they're talking about. So probability spits out a measure for events. So you can say it's kind of measuring the weight of the event, or it's measuring the size of the event, but you know, it's a little different than that, right? It's measuring the probability, which is kind of like the weight or the size, right? So it's measuring something about the event, right? So it's a numerical measure, of course. Most measures are. It's a numerical measure of what? Of the likelihood of that a specific event will occur. But that's a little bit circular statement, right? Because you could say probability and likelihood. What's the difference between those two, right? If you don't know what probability means, you don't know what likelihood means. If you don't know what likelihood means, so it's not really helpful. But at least this part is true. It is a numerical measure on an event. Okay, they're trying to give you some intuition here, but that is kind of circular, right? Okay, now, some property. So, now what do we mean by P of E? What does this notation mean? That's the probability of that event. So what are they saying here? Now, E sub I means like any event. So they're trying to make a general statement here. They're saying that for any event, something. So what are they saying? For any event, the probability will be what? Between what and what? 0 and 1, right? And they're saying that's true no matter what. Now, they're not telling you, the probability of this event is this. They're not making that kind of statement. They're making a statement saying, no matter what the event is, we can make this statement. And what is the statement? That it's always going to be between 0 and 1. Now, if you accepted this as the rule for a probability, which isn't always true, but if you did, then you can see that that's definitely going to be true. Why? You're saying that it's never bigger than 1, for example. That's one thing that they're saying. It's never bigger than 1. Why is that definitely true? Because for this to be bigger than 1 would mean that this is bigger than this, right? But that would mean you have more elements in E than in the subset, and then in the sample space, but you can't, because E is a subset of the sample space, right? You can't have more elements there than here. So this will never be bigger than 1. So that's one part of it. And then the other part is that it's always greater than 0. Well, these are numbers. I'm sorry, we're counting. You don't get negative elements, negative number of elements, right? And you don't get negative number of elements here. So these are never negative. So their ratio will never be negative. So that's one way. But as I said, that formula isn't always true, but that's one way to see this. So that's called the first property of probability. I'm not sure about the A here. What's the difference between E, S of I, and A? What is that? Oh, thank you. Okay. So she said, she reminds us that E stands for elementary events, and A is compound events. So in any case, though, they're both are going to be held true. Now, that's all we have time for today. So I'll try to, I'm not sure if I'll try to adjust our homework according to what we covered or not. That's all we have time for today, though. And I think I'm not going to bother publishing this recording because it wasn't really done on the screen, so it's going to be kind of just a verbal